Warning: sulfuric, nitric, and hydrochloric acid are corrosive. Dimethylformamide and methyl tosylate may be toxic. Wear gloves when handling them and work in a well-ventilated area. Hi guys, here is MIH. Lucigenin is a complex aromatic molecule which emits green-blue fluorescence under UV light. But what makes it especially unique compared to other fluorescent molecules is that its fluorescence can be influenced by many substances in a living organism. For example, superoxide ions produced by cellular respiration react with lucigenin to generate light, while chloride ions can quench its fluorescence. These properties make lucigenin useful as a fluorescent probe in biochemical assays to quantify enzyme activities and study metabolic processes. I might try these types of experiments in the future, but the main reasons I wanted to make lucigenin was because of its interesting synthetic route that features a series of classic organic reactions. Starting from N-phenylanthranilic acid, an intramolecular Friedel-Crafts acylation catalyzed by sulfuric acid affords acridone, which then undergoes N-methylation to give N-methylacridone, before reductive coupling and oxidative aromatization to produce lucigenin. The first step of the sequence can be found on organic syntheses, and a paper from Journal of Chemical Education even turned the synthesis route into an organic chemistry experiment suitable for undergraduates, which made me believe that the synthesis is robust and simple for me to give a try. Although I did find that some experimental procedures in the paper did not work, and only managed to produce less than a gram of crude lucigenin from 10 grams of N-phenylanthranilic acid, I would still say that the synthesis was fun and definitely worth a shot. For the first reaction, I weigh out 10 grams of N-phenylanthranilic acid, also known as phenamic acid. The compound is noted for being used in quantitative determination of vanadium, and can be prepared from O-chlorobenzoic acid and aniline by an organic synthesis procedure. I add it to a small flask, and then weigh out 40 grams of 95% sulfuric acid in the same beaker. My acid is slightly orange due to impurities, but the reaction will still work. The moment the sulfuric acid is added to the flask, a beautiful olive green color appears, which is the color of protonated acridone. The flask is stoppered to prevent moisture from entering, and placed on a beaker of boiling water for 1 hour. Initially, the heavier sulfuric acid sinks to the bottom of the lighter N-phenylanthranilic acid, but after I swirled the mixture, they seem to mix evenly to a brownish yellow liquid. The organic synthesis procedure required 4 hours of heating and obtained a yield of 91 to 96%, but the paper I'm following only needed 1 hour and apparently also had a decent yield of 80%. Since I'm rather short of time, I decided that a slightly lower yield is acceptable. After an hour, the color of the mixture changed to have a slightly greenish tint, and the heating is removed. Meanwhile, I added around 100 ml of water to a large beaker and heated it to 80 degrees C. The paper called for boiling water, but I found that 8 degrees C water is safer to work with as it reduces splattering. I carefully poured the reaction mixture into water, and as I expected, a violent reaction happened as sulfuric acid releases much heat when diluted with water. A bright yellow solid is formed immediately, which is our product, acridone. Now I'll explain why I deliberately used hot water instead of the much safer cold water. The conventional workup procedure of such reactions with concentrated sulfuric acid uses ice water as the exotherm is well controlled, but this reaction is special in that some sulfonated acridone byproduct is formed, which can be hydrolyzed back to acridone in boiling water. Thus, using hot water instead of cold water can increase yield while conserving time of heating the solution up again. After all the reaction mixture is poured into water, the large beaker is placed on a heating mantle to boiling its contents for 5 minutes, serving to hydrolyze any sulfonated acridone as mentioned before. While this is underway, I added a bit of water to the original flask and placed it under an UV lamp. You can see that the water underneath has no fluorescence, but the contents of the flask emit an intense and beautiful blue fluorescence, proving that our reaction is successful. Although acridone is almost insoluble in water, the suspension still emits such a strong fluorescence, demonstrating the potency of the compound. Interestingly, the mixture in the large beaker doesn't display such a bright fluorescence, probably because of concentration quenching effects. After the 5 minutes of boiling, the mixture is suction filtered to isolate the insoluble acridone from most of the sulfuric acid. The resulting filter cake is transferred back to the beaker, and a dilute sodium carbonate solution is added. The mixture foams quite a lot as residual sulfuric acid is neutralized by the carbonate. After bringing this mixture to a boil for another 5 minutes, it is again filtered. The filtrates of these two procedures may contain a small portion of acridone product as well as unreacted N-phenylanthranilic acid, but it is not worth recovering. The acridone is washed with some water for 3 times before finally dried in air. The final yield of crude acridone is 5.52 grams, representing a 60.3% yield. Boiling for 4 hours would definitely increase this yield, and some product is inevitably lost in the repeated washing processes. Nonetheless, this amount of acridone is more than enough for the next step, which is methylation on nitrogen to afford N-methylacridone. For such methylation reactions, a one-pot procedure is most common with substrate, methylating agent, and base all added together. However, the paper used a two-step approach, first reacting acridone with potassium hydroxide and ethanol to produce the potassium salt, and then methylating it with methylaldehyde and DMF. I weigh out 1.3 grams of potassium hydroxide and dissolves it in around 70 ml of ethanol. I then heat it up while adding 4.1 grams of my crude acridone. This is where things went wrong a little. The paper said that acridone dissolves in hot ethanol KOH to give a clear yellow solution, but I found that things just don't want to dissolve. Although you can see that the ethanol takes on a darker yellow color, which is probably the acridone anion, the majority of acridone still suspends in solution. I boiled the mixture for half an hour and tried adding more potassium hydroxide, but the solid still didn't dissolve. I decided to take a small sample of the resulting slurry and directly proceed to the next step. Surprisingly, I found that the yellow slurry dissolved very well in DMF, and the solution even emits a greenish fluorescence. As acridone is insoluble in DMF, the slurry I have here must be the potassium salt of acridone. In other words, the deprotonation worked, but the paper was wrong in that the resulting salt doesn't dissolve well in ethanol. I then added a milliliter of methyl tosylate to the DMF solution as the methylating agent. Methyl tosylate is a less known reagent than methylaldehyde or dimethyl sulfate, and I choose it because of its much lower cost and toxicity than the other two options, while still being reactive enough for our reaction. The reactivity and toxicity of methylating agents are essentially proportional, but the volatility of the reagent should also be considered as a part of safety measures. Methylaldehyde boils at 42 degrees C, but methyl tosylate boils at 165 degrees C, greatly lowering the risk of inhaling vapors. The mixture is then heated on the hot plate for 5 minutes. Initially, remaining ethanol in the acridone salt boils off, and later some fumes of dimethylamine is formed from the DMF decomposing at high temperatures. I removed the heat and added a lot of water to precipitate our product, N-methylacridone. A pH test shows that no alkali remains, indicating that the potassium salt is indeed consumed in the reaction, and the methylation is probably complete, although I cannot be sure. With the new reaction conditions in hand, I proceeded to convert my remaining acridone salt. I first measured out 30 grams of DMF and added it to the acridone salt. The ethanol in it had evaporated and the surface of the salt turned to a beautiful orange color. The salt dissolved readily to afford a dark yellow-brown solution. I then added 10 ml of methyl tosylate, which is in excess to the acridone, into the solution, and no reaction seemed to take place. The paper mentioned that methylaldehyde can react at room temperature, so I assume that it's because methyl tosylate is less reactive. Just like before, the solution is heated on a hot plate, and its color becomes lighter while remaining ethanol is rapidly boiled off. I assume the dark-colored acridone anion is reacting with methyl tosylate to afford N-methylacridone with a slightly lighter yellow color due to its lesser extent of conjugation. However, as the solution is heated more, the color appeared to be darker again. I took a small sample, added it to water, and tested the pH to determine if the reaction is complete, and the neutral pH shows that the acridone salt is consumed. Just like before, I take the reaction mixture off heat and pour it into water, and a light yellow precipitate immediately appears, which has a different color from our acridone starting material in the Petri dish, showing that the methylation reaction probably worked. In total, I used about 200 ml of water to dilute the reaction mixture and remove most of the DMF and potassium tosylate, and now everything is suction filtered. N-methylacridone is also insoluble in water, so a few water washings are done to remove remaining DMF and salts. The next video will feature the conversion of N-methylacridone to lucigenin via a zinc-mediated reductive coupling and an oxidative aromatization, so stay tuned for that.